The title of my presentation of my paper is a first principles study of lithium-ion mobility in cubic LLGO solid electrolyte at elevated temperature, because we used the temperature more than 750 Kelvin. And these are the authors, and I appreciated the help Dr. Han and Dr. Dimitri um, throughout the semester, and the support they give me when I was writing the paper. So, what is the aim of this project? The aim of this project was basically the main aim was to observe, and from there we can calculate the activation energy, and from that electrolyte at room temperature. That was the primary goal of this project. Many researchers or many groups they performed this kind of simulation, but those experiment or those papers were not that much explicit like we did. So we showed explicitly how we can measure the ionic conductivity from the diffusion pathway, and that was the unique and easiest way to find the ionic conductivity. This is the method I followed for this paper. So we observed the migration pathway and calculated the ionic activation energy. From there, the ionic conductivity. And to do so, to find the migration pathway, what we did, we go through the DFT, molecular dynamics. Then we create a movie to observe the pathway, how it diffuses. Does it hops, or does it make a jump from one side to distant side? And here we observe the migration pathway rate, at which time the lithium makes the jump, or it changes its side to another side, its position to another position. And from that rate, we calculated the ionic conductivity, activation energy, and ionic conductivity. So,
I interrupt?
That already I said, EFT.
Raju?
Hello?
Yeah, yes. I think we have problems with the sound. It's really almost impossible to hear. Like my students say it's like you sound like a robot.
Okay.
Low speed internet.
Maybe, I think so.
Maybe we can try disable camera, and if it doesn't help, then I will start showing your slides and you will only speak. Let's first try to just disable your camera and try to say something.
Okay, so let me disable my camera.
Like stop video in the lower left.
Does it clear? Is it clear now?
For me,
well, now it is better, but not necessarily that it would be.
Okay, and if there will be more problems, our next level backup, someone else like myself will show slides and you will speak. Roger, since we made a break, let's generally plan to ask questions in chat line, but I have a very quick question to two questions to your previous slide.
Previous slide?
Previous slide.
Okay.
So, and some of the audience will may ask the same question to you later. So, why are you using molecular dynamics rather than transition state search? It's question number one. And comment number two, for understanding your problem, you may highlight that the model has a lot of vacancies. Otherwise, it would not work. Would you please briefly address these two things right now?
Dimitri, can you please repeat again because the sound was not clear?
Okay. So first one, why you are using molecular dynamics rather than transition state search?
Because we are interested to see the movement of the ions. The transition state, I think, is related to interested in electronic properties. We are interested to observe the movement of ions.
Mm-hmm. Okay.
Okay.
Yep. But later on, we should return to this question because reviewer of your paper may ask the same. Okay. Please continue. So for this paper, the methodology we used, these are the important equations that I have used. For the density functional theory, we used the Consham density function theory equation. Then for the molecular dynamics, we used Newton's law, and we also used a radial distribution function to observe the distance between ions. And although we use the electronic properties to observe actually the band gap or the absorption spectra, but for this project, already the thing I was telling I just expressed regarding the question about Dr. Dimitri, that we are interested in the movement of ions, not the movement of electrons. So after that, and from that point of view, from the molecular dynamics, we observe the time it makes first transition, the first movement, that we took as a rate, that at which at the point it makes the movement or it changes the position, and using that rate we calculated the ionic conductivity of our model we used for our study purpose. So you can see the red, our point of interest. The movement of these blue atoms is the main interest of our study. We want to see the movement of these blue atoms. So, and we used eight PFU, that means per formula unit. That means the original cell, the cubic cell is the formula is Li7, La3, Zr,
ZR2 and O16. So if I multiply by 8 formula unit, it become lithium 56, lanthanum 24, zirconium 16, and oxygen 96. So how the mobility of the lithium we'll discuss how the lithium ion, how the mobility of the lithium ion is connected with the concentration of the vacancies. We'll discuss later. So let's just see a movie that we have created from our molecular dynamics. So this was I don't know why it's not working. It was working before for 1000 Kelvin. Let's watch the movie for 1500 Kelvin. Sorry, my connection at home is not that much good. So you see, this is the lithium ion. We are tracking the movement of this lithium ion. This will move from this side to this side. And this movie was made for 15 femtoseconds. So you see, it's just started vibrating. So still it it is in original position.
Roger?
Yes. Now you see, it just changed its position.
But on my screen, it doesn't show any movie. I don't know. Maybe it's different on for other attendees.
I see also Dr. Han said can't see the movie. Uh, I think because of the internet connection problem.
Okay,
That's why.
then Roger, let's try.
No.
If I will show your slides,
Okay.
maybe it will be a little quicker.
Yes.
Then please stop sharing, and I will start sharing. Do you see anything happening?
No, yeah, I see.
Okay, please continue the story and let me know when there will be time for next slide.
Yeah, just run the movie for the 1500 Kelvin. So at the initial time, this is it is in its initial position. So it just started to vibrate, and you see it just making the transition. Uh, so in the it was for a short period of time. It was in the transition position. Now it moved to the its final position. I think you can stop here, Dr. Vijay. Then go to next slide. So as we observed that for all the lithium atoms, this similar phenomena is obvious. So we tried to take a single lithium atom to explain our phenomena. So that's why we took a single lithium atom. So you can see at the left-hand figure the A, B, C, D 3D figures. You can see in in A, the blue atom, that is the lithium atom is our point of interest. Please let me clear that we didn't show the lanthanum and zirconium atom here because throughout the movie and also you will see from the RDF the lanthanum and zirconium atoms are almost fixed in their position. So we ignored to for our clear visualization. So you can see at the very beginning, the 0 Kelvin, the blue atom at its original position. As we increase the temperature at 300 Kelvin in B, so it makes a little movement, but it is still in the original position. It just start to vibrate. And when we increase the temperature to 1000 Kelvin, it hops, it changes its position to the neighboring atom, the neighboring position. And when we further increase the temperature to 1500 Kelvin, you can see it again changes its position to side 3. You can, from the right side figure, you can see at the original position is at A, in which we indicate the position as site 1. Then at 1000 Kelvin, it changes its position to site 2. And when we increase the temperature at 1500 Kelvin, it changes its position to site 3. What is so special about this material? Because this is the dielectric material we want to use for our lithium battery. Um, uh, I don't know the lithium chloride crystal, but it will move through the lithium metals. If we use the two electrode as anode and cathode, lithium as a metal, and we put the lithium LLZO electrolyte in between, then the lithium ion makes a movement from anode to cathode. That's we can discuss if we have time.
Can I briefly comment?
Yes, when we apply a potential, then from the anode side, the lithium ion makes the transition from the anode to cathode through this LLGO, and this is the electrolyte we used as a dielectric so that it doesn't make short circuit anode and cathode. But
Roger, please correct me. Is it correct that the main structural feature of this material, which determines this property, is that this material is, so to say, porous, that it has a lot of vacancies, empty spots
yes,
where lithium is missing, and
yes,
therefore lithium ions can move to vacancy.
yes, yes.
So it should be declared right at the beginning. It's a very critical. It seems critical point of this material.
Yes, that's why we are interested in this material. That's why the lithium ions from the anode makes the transition to cathode through this material because of the vacancy.
Okay.
This material can have 120 20 lithium atoms, but we see it has a vacancy, and it has 56 lithium atoms. Are you clear?
Yep.
So next slide. So uh, so from the molecular dynamics in the movie, we showed that at the initial position it was at site 1 at 300 750, still in 700. We increase the temperature to 750 and we see it still retains its original position. It didn't move. So we further increase the temperature and we see that at 1000 Kelvin it makes a movement from site 1 to site 2, and with further increase at 1500 it makes further movement from site 2 to site 3. Yes, the material is charge neutral. How do you make vacancies of the lithium ions keeping in itself neutral? It's already the structure is already vacant. Um, uh, if we see the chemical structure of this material, it has two structure. Um, IA3D, that means cubic structure, and I for one 4D, tetragonal structure. So we are talking about the cubic structure, and for the cubic structure, this material, the lithium ion, it has uh, two sides, or some can say three sides, depending on the position. But for our material we used, there are two sides. There are one tetragonal side and octahedral side. Okay, so the tetragonal side can have 24 electrons, sorry, 24 lithium atoms, and the octahedral side can have 96 lithium atoms. So 24 and 96 makes 120 lithium atoms that can be available in this structure. But by default, this uh, solid LLG structure has 56 lithium atoms. So it's already vacant position available there. Does it make sense? Yeah, actually, we are not dealing with the tetragonal phase. That's why we are not interested in the phase changing, because we already took the cubic structure. But that's a very good question, because in general, in practical scenario, in reality, uh, at room temperature, you cannot have the cubic phase structure. You always have tetragonal phase structure. So when you increase the temperature around 700 to 800 Kelvin, it make the transition from tetragonal to cubic phase. But for our project, for this experiment, we used cubic structure. Yeah, so far it's neutral. It's stoichiometric neutral, but it is porous because it has vacancy. So next slide. Can you go to previous slide, Dr. Dimitri? I didn't discuss the right side picture. The At the right hand side, um, you can see the ultimate position of the lithium atom. So at 300 Kelvin, you see four oxygen atom is connected to lithium atom. That means it is in tetragonal side. As well, for 750 Kelvin, it is also occupies tetragonal side, but you already seen that when it we increase the temperature to 1000 Kelvin, uh, um, it make a jump and it changes its position to neighboring position. Still, it is in tetragonal side. But when we increase the temperature further to 1500 Kelvin, the ultimate position it regains, it is octahedral side, because you can see there are six atoms. Six atoms are connected. Actually, there are eight. I don't because of the um, picture you cannot see the other two. So it it occupies the octahedral side at the end of the 15 Kelvin temperature simulation. So from this point of view, we can say this lithium atom moves from its original position to neighboring position, okay, and it also moves to the position which is back end. That means whether it is octahedral or tetrahedral, it moves to the position which is back end. So next slide. Yes, uh, yes. Maybe I missed some. Actually, maybe I didn't uh, explain something in the introduction. What I need to do. Uh, that's why it's becoming hard for the audiences to understand. Sorry for that. So if you make a question, then I can make clear if I had missed something. Sorry for that. So after from this molecular dynamics, we calculated the distance covered by the lithium ions. So that the displacement that makes by the our observing lithium ion at 300 Kelvin, you can see this is just a vibration. We didn't take this as a displacement. Why? Because we took our unit cell as almost 12.98 angstrom. Okay, so for each cell, the distance is almost 1.3 or something like that. So when we observe the displacement of the lithium atom is more than 1.2 or 1.3 angstrom, then we take it as a displacement, as a movement. So that's why, and also from the movie, it was clear that at the initial position, it was just making the vibration. It was not moving from its original position. So you can see at 300 Kelvin and 750 Kelvin, it doesn't make a move. It just start to vibrate. But when it is 1000 Kelvin, at you can see at 3500 femtosecond, it makes a jump. At C, you can see at 1000 Kelvin. Okay, and uh, if we further increase, we can see that the jumping time is decreasing. So at 1000 Kelvin, it jumps at 3500, but at 1250, it jumps around 2000 femtosecond. And at 1500 Kelvin, it jumps around 600 femtosecond. And at 1750 Kelvin, it jumps around 1000 femtosecond. So, why with the increase